Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to solve a titration problem where you're asked to use a redox reaction. So let's get into this. So in this problem we have the reaction. So they're giving us this reaction here, and they're saying that this reaction is used to show the sulfite ion concentration present in wastewater from a paper making plant. So, and then they tell us if 25.00 milliliters of this wastewater requires 31.46 milliliters of a 0.02237 molar KMnO4 for its titration. What is the molarity of the sulfite in the wastewater? So, what they're asking for is what are they giving us? They're giving us the 31.46 milliliters of a certain molarity. So we have a molarity of KMnO4 that's being used to titrate a certain amount of wastewater, so 25 milliliters. So you've got your 25 milliliters in your Erlenmeyer flask. You've got the KMnO4, the potassium permanganate solution in your burette. It's got this molarity. We're going to titrate it. We're going to add our KMnO4 to the Erlenmeyer flask until it reaches the end point. At that point, they say that we've added 31.46 milliliters. And so what we need to do is we need to start with the 31.46 milliliters and convert that to moles, right? And then we could use the mole ratio from our balanced equation to then convert moles of KMnO4 to moles of the sulfite in the wastewater, in the 25 milliliters of the wastewater. And then we can figure out the molarity. Remember that molarity is moles. Molarity is equal to moles of the solute over liters of the solution. Okay, so right now we have milliliters. They're giving us milliliters of the solution, right? So we can convert that to liters. But what we need to find out is the moles of the solute, which is the sulfite. So we can use the information given here, the milliliters and the molarity. We can use molarity to convert our volume of the KMnO4 used to get the moles. And then we would use our balanced equation here to convert moles of your MN2 or MnO4, your MnO4 to get moles of your SO3. Now, here's the thing. We don't have a balanced equation here. So we have to balance the redox reaction here first so we can get a balanced equation, and then use the stoichiometry using the balanced equation to convert to moles of the sulfite in your wastewater. So we got to do that first. So when you're balancing the redox reaction, it's a little different than balancing a normal reaction. There is some similarities, but there's some extra things you need to keep in mind as well. So the first thing we need to do is find the oxidation states or oxidation numbers of each element in all of the species that we have, all of the compounds and elements that we have here. So first we have sulfur and oxygen. Oxygen, according to the rules of assigning oxidation states, when you have a polyatomic ion like this, oxygen takes precedence over sulfur. So we're going to assign the oxidation state of -2 for oxygen, which is the normal expected oxidation state of oxygen. So that's going to be a -2. And I want to point out here that notice that I'm putting for oxidation states, I'm putting the plus and minus first before the number. For the charge, it comes after the number. So that's a good indicator of when you have an oxidation state versus a charge, right? So if you're trying to write the charge of something, we write the plus and minus after the number. If it's an oxidation state or a formal charge or something like that, usually it's going to be before the number. So we write the plus and minus first and then the number, right? So that's just a technical thing that I just want to make clear. Okay, so we know that oxygen, we're giving oxygen a oxidation state or number of -2. We have three oxygens, so each oxygen has a -2 oxidation state. So that's a total of a -6. One of the rules of assigning oxidation states is that the total number of oxidation states added together must equal the charge on your ion if there is a charge. If there is no charge, then it's got to add up to 0. But here we have a charge of 2 minus. So that means that when I assign the charge or the oxidation state to sulfur here, it's got to be such that when I add it to -6, I get -2. And so that works out if I have a +4 on the sulfur, right? So 6 total, -6 total for the oxygens. I only have one sulfur. So in order to have a -2 or 2 minus charge, I have to have a +4 because +4 and -6 gives me the 2 minus. Okay, so that is the oxidation state of sulfur. Same thing here. So I'm going to give, for this polyatomic ion, oxygen is going to take precedence. So I'm going to give oxygen a -2 oxidation state again. Here I have 4 oxygens, so 4 times -2 is -8. So I have a total of a -8. Again, I have one manganese. So the oxidation state on the manganese has to be such that when I add it to -8, I get -1, right? So that means that this has to be a +7 because +7 minus 8 gives me the -1. So now I have the oxidation states of manganese and oxygen. So I'm going to erase these. Now for sulfate ion, again, just as with the sulfite ion, oxygen is going to take precedence. So I'm going to give that a -2 oxidation state. I have 4 oxygens. Each oxygen has a -2, so that's going to be a -8 overall for the oxidation states of oxygen. And again, sulfur needs to have an oxidation state such that when I add it to -8, it gives me a 2 minus, right? So what is that going to be? That's going to be a +6. So +6 minus 8 gives me a 2 minus charge. So that's going to be the oxidation state of sulfur. So I can go ahead and erase this. And finally, for manganese, the rule is if you have a monatomic ion, then the oxidation state is the same as the charge. So I have a 2+ charge on manganese, so it's going to be a +2 oxidation state. So now I've determined what the oxidation states of each atom in each substance is. And now I can determine oxidation and reduction. This is a redox reaction. So therefore, something's being reduced and something's being oxidized. So I have to figure out what's being oxidized and what's being reduced. And so the mnemonic devices that are good to remember is oil rig and or Leo Gur. Either one of these is useful. Oil rig. Oil is oxidation is loss of electrons. Rig is reduction is gain of electrons. Leo Gur, same thing. Leo, loss of electrons is oxidation. Gain of electrons is reduction. So either one of those mnemonic devices is helpful. So what does this mean? So oil, oxidation is loss of electrons. So I have to figure out what lost electrons, what element lost electrons. If you lose electrons, that means you become more positive. So if you go from reactant to product and you become more positive, that means you lost electrons. So what became more positive? Sulfur, I have a +4 here, and on here I'm about +6. So it became more positive. It lost electrons. So that underwent oxidation. Okay. So I'm going to split the oxidation and reduction into two half reactions. So I'm going to divide these and separate them from each other and deal with them separately. So I'm going to do reduction over here. And then over here, I will do oxidation. I'll write it here. Oxidation. Okay, so we said that the sulfur has got oxidized because it lost electrons. Oxidation is loss of electrons, and we can see that by the fact that it became more positive. So becoming more positive means you lost negative charge, right? You lost the negative electron, so you became more positive. So therefore, SO3 2 minus and SO4 2 minus are part of the oxidation half reaction. These are called half reactions. We're dividing them in half. So oxidation we'll have over here. So SO3 2 minus goes to SO4 2 minus. So here's my half reaction for oxidation. And then for reduction, remember reduction is gain of electrons. If you gain electrons, that means you're going to become more negative or less positive. So which one became more negative or less positive? Here we have a +7 on manganese, and we have a +2 on manganese. So it became less positive, or in other words, more negative. So it must have picked up electrons. So gained electrons. So that's the reduction half reaction. So we're going to write that half reaction over here. MnO4 minus is going to go to Mn2 plus. Okay, so now that we've divided the overall reaction into the half reactions, we have the reduction half reaction over here. We have the oxidation half reaction over here. So now what we're going to do is balance both of the half reactions together but separately. So when you're balancing redox reactions, the first thing you want to do is balance the number of atoms. Second, balance the charge. Okay? And then third, make sure that the electrons on both sides are equal, right? So we're going to balance the number of atoms like we normally do. That's what you normally do when you balance your equations. And then in addition to that, we're going to have to balance the charge. And the way we balance the charge is by adding electrons. And then once you add electrons, you got to make sure both half reactions have the same number of electrons. So those are the 3 steps. All right, so step 1, let's balance the atoms. So over here we have SO3 and we have SO4. So here we have sulfur is equal on both sides, but the oxygens are not. Now we're not paying attention to charge. Charge doesn't matter at this point. We're just balancing the atoms. Okay, so I have 3 on this side, I have 4 oxygens on this side. Well, how am I going to balance the oxygens? Well, this comes in when you have acid solution, right? So the fact that we're in an acidic solution here helps us. So the way we're going to balance the oxygen is by balancing it with water. Since this is in an aqueous solution, you have water molecules. So since I have 3 oxygens on this side and I have 4 on this side, I have to balance with the water on this side. So I have to add 1 water molecule on this side. So now that I have one water molecule on this side, I have four oxygens, but now I have two hydrogens on this side. So now I have to balance with hydrogens on this side. And again, the fact that this is acidic solution means that we have H plus ions in solution. So we're going to use H plus ions to help us balance the equation. So on this side, I'm going to add two H plus ions. And so now it's balanced. I have equal number of atoms on both sides. So let's now go over to this half reaction. Same thing. We need to get atoms equal on both sides. So here I have one manganese, but here I have four oxygen. So I'm going to need four oxygen on this side. So I'm going to add four water molecules. So add 4H2O. Okay. Now that I have four oxygens on this side, it's balanced with this four oxygens. But now I have 8 hydrogens. I have 4 times 2 is 8 hydrogens. So again, I'm going to have to add 8 hydrogens on this side to balance. So I'm going to add 8 H plus ions. So now I have 8 hydrogens on this side, and that's going to balance the 8 hydrogens on this side. So it's balanced. So now the next step is, now that both of these reactions or these half reactions are balanced with regard to the number of atoms, I now need to balance the charge. So on this side, I have neutral water plus one of these, and it's a 2 minus charge. So over here, I have a total of a 2 minus charge. And over here, I have a 2 minus charge. But I also have a 2 plus charge over here. So I have a plus charge on my hydrogen, but I have 2 of them. So the 2 plus charge here balances the 2 minus charge. So I have 0 charge over here, but I have an overall 2 negative. I have to add electrons to the side that is less negative, right, or more positive. I have to add it to the less negative or the more positive side in order to get it to balance. So since this is neutral, I have to add 2 electrons this side. So I'm going to add 2 electrons to this side. Okay, so now I've balanced the charge on this side. So I'm going to do the same thing over here. So let's calculate the charge. So here I have 8 plus hydrogen. So I have 8 positive charges over here from the hydrogen. So that's 8 plus, or a positive 8. I have 1 permanganate ion. So that's a negative 1 here. So negative 1 plus the 8 gives me a positive 7. So I have a positive 7 total on this side. But here I have neutral water, that's 0. And here I have a plus 2 charge on the manganese. So over here I have a total of a 2 plus charge, right? So in order to get this balance out, I have to add negative electrons. So I'm going to have to add negative electrons to the more positive side to get it to balance out. So since this is a positive 7, I'm going to have to add 5 negative electrons to get this to positive 2. So I'm going to go ahead and add 5 negative electrons. So I have 5 negative electrons here. Now this has a positive 2 overall charge. So now it is balanced, both sides according to charge. So now the last thing I need to do is make sure that both half reactions have the same number of electrons. Notice that I have 2 electrons on the product side here, and I have 5 electrons on the reactant side here. So if I can get these number of electrons equal, they will cancel out because they're on opposite sides of the equation. This is on the reactant side, this is on the product side. So what I'm going to do is I'm going to add these 2 half reactions back together, but before I can do that, I need to get the electrons to cancel out. So here I have 2 electrons, here I have 5. So if I multiply this equation by 5, I'll get 10 electrons. And if I multiply this equation by 2, I get 10 electrons. So then let's do that. So then here, if I multiply this by 5, I'm going to get 5H2O plus 5SO3 2 minus 5SO4 2 minus plus 10H plus 10 electrons. I do the same thing over here. I have 2. I'm going to multiply everything by 2. So here I'm going to get 10 electrons plus 2 times 8 is 16, 16H plus, again, 2 times this is going to be 2 MnO4 minus. And so I got 10, 16, 2, and then I've got Mn, so 2 times Mn, that's going to be 2 manganese ions, plus 2 times 8 is 4. 2 plus 4 is 8, so I have 8 H2O. Okay, so now that I've got that done, now it's time to add these two half reactions together. But I have to cancel things out that are on the reactants and product side. So if you have the same thing on the reactants and product side, you can cancel things out. So just like with the electrons, so I have 10 electrons here on the product side. I have 10 electrons here on the reactant side, so that can cancel out. What about H plus? So I have 16H plus here, and I have 10H plus here. So the 10 over here can cancel out with 10 over here, leaving me 6 on this side. So I'm going to cancel those out, and then I'll erase the 1 here. That'll give me 6H plus left over. The MnO4 is fine. That's not the same on both sides. Mn, that's fine. What about water? We have 8 waters on the product side over here. We have 5 waters on the reactant side. So these 5 waters can cancel out with 5 over here. So we can get rid of that, and then this will become a 3. So now that we've canceled everything out, oops. Sorry about that. Now that we've canceled everything out, we can add the equations back together. So we're going to put reactants on reactants together, products with products. And when we do that, we get 6H plus 2 MnO4 minus. So those two plus this one plus 5 SO3 2 minus. And then that's going to give us these two products. So we have 2 Mn2 plus 3 water. And then we got product on this side, so plus 5 SO4 2 minus. And so that, ladies and gentlemen, is our balanced redox reaction. And now that we have our balanced equation, we can now use this equation to do stoichiometry and figure out the molarity of the KMNO4. The molarity of the sulfite in the wastewater. Okay, so as I said before, we're given 31.46 milliliters of the KMNO4. So we know that to be the case. We know that that is what was used to titrate the wastewater. So we're going to start with that. And anytime you're given molarity, you can use that as a conversion factor. So let's go ahead and start with the given. So we have 31.46, 31.46 milliliters of the KMNO4. Okay, and we're going to put that over 1. And then we need to get to moles of the KMNO4. Why? Because anytime you're converting from one thing to the other using stoichiometry or just in general, you got to use a mole ratio, right? So here they're giving us a certain amount of KMNO4. They want us to find a certain amount of the sulfite ion. So anytime you are converting from one substance to a different substance, you're going to have to use a mole ratio to do that. So you got to convert to moles. So any way you can, convert it to moles. Once you get moles, you can use the mole ratio to convert from moles of one thing to moles of the other thing. And then convert those moles to whatever unit they're asking for. So in this case, we're just trying to find molarity. So we just need the moles of the sulfate or sulfite ion in the wastewater. So we got to convert this to liters because we can use molarity to convert liters of solution to moles. So there we go. So, but first we got to convert milliliters to liters. So I know that 1 milliliter is equal to 10 to the negative 3 liters, or 1/1000th of a liter. How do I know that? Because I know milli, the prefix, means 1/1000th of. So 1 milliliter is 1/1000th of a liter. Now you could use 1,000 milliliters is equal to 1 liter. It's the same ratio. So if you want to use that, you can go ahead. I'm going to use milliliters. 1 milliliter on the bottom. So this is going to be KMNO4. Don't forget the substance so we know what we have. MNO4. So milliliters of KMNO4 on the top and bottom cancel out. Now I have liters of KMNO4. Now I can use the molarity. Molarity is moles over liters. So this is telling us that 1 liter of the KMNO4 solution, and here we're talking about solution here, has 0.02237 moles. So 0.02237 moles of the KMNO4. And liters of the KMNO4 solution are going to cancel out. And now I have moles of KMNO4. Now I can convert that to moles of the sulfite using my balanced equation. So here I have, for every 5 moles of your sulfite ion, I have 2 moles of the permanganate ion needed to react with it. So it's a 2-to-4 ratio. So there's my mole ratio that I'm going to use. Okay. Now, for those of you who may be concerned, it's like, well, wait a minute, Mr. Cobalt. We have the permanganate ion here, but here we have potassium permanganate. Is it the same thing? Well, you'll notice here that for every one of these KMNO4 units, you have 1 permanganate ion. So it's a 1-to-1 ratio anyway, so it doesn't matter. So in this case, we don't have to worry about it. So here, one KMNO4 is the same as 1 KMNO4 here. So the mole ratio, whether we use KMNO4 or MNO4, it doesn't matter. So here I have moles of KMNO4 on the bottom, so I'm going to put 2 moles. I have moles of KMNO4 on top. I'm going to put 2 moles on the bottom. So 2 moles of KMNO4 on the bottom, and 5 moles of the sulfite ion on top. So 5 moles of SO3 2-. And now moles of KMNO4 cancel out. And I am done. I have moles. So now to calculate the moles of sulfite in 25 milliliters of the wastewater, all I need to do is multiply by, on top, divide on the bottom. I get my answer. And when I do that, I get 0.0017594. 17,594. So 0.0017594 moles. Let me double check that. So 17,594. Yes. So this is moles of SO3 2 minus. So now that I have the moles, we have to double check our sig figs. So remember, the number of sig figs in your answer should be the same as the least number of sig figs in your measurements. This is the rule for multiplying and dividing. So what's the least number of sig figs? So we have 4 here. This is exact, so we can ignore that. This is 4 here. This is exact. We can ignore that. So the least number is 4. So we should have 4 sig figs. So ignoring these zeros, these are not significant. We have 1, 2, 3, 4. So I'm going to underline the 9. So the 9 is our last significant digit, but I'm going to keep an extra one just to be safe. I don't want to have a rounding error. So now, what are they asking for? Let's go back. So what is the molarity of the sulfite? So remember, molarity is moles divided by liters. So they gave us 25 milliliters. We need to convert that to liters. So we're going to take the 25.00 milliliters over 1. Again, 1 milliliter is equal to 10 to the negative 3 liters. And so milliliters are going to cancel out. And then I get 0.02500 liters. So now that I have liters, all I need to do is take the moles divided by the liters, and I get my molarity. So 0.0017594, and that's the moles of the sulfite ion over 0.02500 liters of the wastewater, right? And then when I divide those, I get 0.07038 molar SO3 2 minus. So that is the concentration of the sulfite ion in the wastewater. And so again, when we're doing our sig figs here, again, since we're multiplying and dividing here, we're dividing. So the rule is that your answer should have the same number of sig figs as the least number of sig figs in the measurements you're dividing. And here we have 4. Remember the line here under the 9 means that that's my last sig fig. I keep the 4 just to avoid rounding errors. So this has 4 sig figs. This has 4 sig figs. The zeros at the end of the number are always significant if there is a decimal point. So these are significant if there's a decimal point. The beginning zeros are never significant. So this has 4 sig figs. So 4 and 4, so the least number is 4. And so I have 4 sig figs here. And that, ladies and gentlemen, is how you attack these sorts of problems. I hope this is helpful. If you enjoyed this video, Or if you learned from this video in any way, then please by all means like the video, share the video, hit that like button somewhere over here. Also, do me a favor, support my channel, subscribe to the channel, hit that notification bell. When you do, make sure you click all. And then last thing, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or problem you need help solving, put that down below. If you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.